Welcome to N is for Networking, the short, sharp podcast where we explain the jargon, acronyms, and concepts of the networking industry in plain language. I'm your co-host, Ethan Banks, a grumpy old network engineer who's been pushing packets around since the 90s. With me is co-host Holly Metlitzky, a university grad with a master's degree working in networking, but new to the scene. In this episode of N is for Networking, we discuss a question that comes from my friend Douglas, a busy college student we definitely want to have on the show once we can align schedules. And we didn't work that out for today. But this question of his, he sent me a whole list, but this question really grabbed me. And his question is, how does bandwidth differ from latency, and why are both important? So Holly, over to you. We gotta talk about some terms first. I mean, bandwidth and latency. So do you have a take on describing networking bandwidth?
For sure. I mean, I think the first thing that comes to mind when I think of bandwidth is, with zero understanding as a young kid, I would run speed tests on my Wi-Fi to see,
Oh yeah.
what's going on there. So, I think about megabits per second or gigabits per second. So really, when I think about bandwidth, I think about, how much data is moving through a network per second, or, in a certain time
Mm-hmm.
frame. Um, Kind of, I guess, if you're pushing something through a pipe.
Yeah, okay. Reasonable metaphors, reasonable analogies. I think there's some nuance to that we're going to get into. But before we do, so if that's bandwidth, what do you think of when you hear the term latency?
Latency, I think of how fast is something getting to you. So if it's left this side at A and I'm listening to it on B,
Yeah.
what is that time difference? For
Mm-hmm.
example, I'm speaking to you now. You might not be hearing me in real time. Could be a couple milliseconds difference to me
Mm-hmm.
speaking and you receiving that. So that would be my understanding of latency.
Yeah, exactly right. That's exactly it. If you were like, I'm in Northeast US, actually you are too, so our latency is probably quite close. We're probably routed through somewhere in Boston, Mass, or New York City, and the latency probably isn't too high between us. I bet as the crow flies, we're just a few hundred miles apart, something like that. But if you or I were talking to someone, say, from here in the Northeast US to India or Australia, something like that, the latency would be much higher because physics. We got to send that signal around the world and back. Okay, so we got a sense of bandwidth. It has to do with speed, how much data we can cram through the pipe in a given amount of time. Latency, how long it takes light to travel between the two of us, depending on where we are on the planet, if you will. And so Douglas asked the question: how do they differ, and why are both important? So I want to dive first into why bandwidth is important, and give a little nuance to your amount of data we can push through in amount of time. Because I think you got it about right, and I think some other people might have a misconception about it. So yeah, the amount of data that can move through a link at a time, more data requires more bandwidth. But you might think, well, wait, if I have a 1 gigabit per second link and a 10 gigabit per second link, the 10 gigabit per second link is 10 times faster, right? Like a speed limit on the highway. Like if I was going 30 miles an hour and then I got a 60 mile an hour speed limit, if I could go 60, that's twice as fast. But it's not actually how bandwidth works, Holly. Can you tell me why?
Yeah, I mean, if you think about it, right, a car has the ability to travel faster. But if we using fiber optics, for example, you're sending ideally everything at the speed of light. So
Right.
it's almost as if the speed of travel is fixed. It's a constant. So you can't increase speed to increase bandwidth, essentially.
Yeah, and if you were to exactly right, if you were to dig into the internals of a physical interface that is sending traffic, it's doing it on clock cycles. Every clock cycle that system rotates through, it gives it another opportunity to send a packet. That's rough. People that know the details know I'm skimming on details, but roughly that's it. And so if you want to go faster, you got to increase your clock speed so you have more cycles upon which you can send data. But right, once that packet hits the wire, technically a frame, if you remember our last discussion,
Yeah.
Holly. But yeah, once that hits the wire, it's going as fast as it's going. Bandwidth gives us more bandwidth per second, gives us the ability to send more traffic, but it doesn't make an individual packet go faster across the link, for sure. Now, another thing that's interesting here is the term throughput. Have you heard the term throughput?
Yeah, as an industrial engineer, I've heard it a lot in a manufacturing context.
Oh,
Not quite
interesting.
not networking, but throughput is the amount of production or whatever you're creating that's going through your production line. So I don't know, boxes per second or whatever it is.
Well, throughput is different from bandwidth in networking. And that's a really good parallel, because throughput is how much data am I actually getting through the line?
Yeah.
Not how much is it theoretically capable of, but how much am I actually pushing through it? And you're going, oh, I've got a 1 gigabit per second line, but I'm only getting 750 megabits per second through. Why? Why is my throughput only 750 meg? Well, it could be impacted by the size of individual packets you're sending. You could send really small packets or much larger packets. That can impact your throughput. It could be there's a series of links between you and your destination, right? Like between you and me, there's a bunch of different routers with different links and different speeds and so on. The capacity of those links could vary in size. Maybe you and I have 1 gigabit pipes at our house off to our ISP. And then the ISP might have bigger links and smaller links, along the way, all depending. That could impact throughput. And then maybe one of those links are congested, somewhere along the way, because there's a bunch of other people sharing them, like a traffic jam kind of thing. That could slow things down for us and reduce our throughput.
Yeah, I actually have, a bit of a question. We can dive into something there when you talk about bigger or smaller links per se. So going from, I don't know, 1 gig link to 10 gig link, what does that mean? How are we physically increasing the size of that link? Is it, is it a cabling thing? Is it, like you mentioned, clock cycle? How is
Mhm.
that done?
That is done at the physical layer. So let's say we're talking about Ethernet. Let's say that the transport is Ethernet. Standards bodies, in this case the IEEE, would define how the electrical and or optical signaling is done so that you can get 10 megabits per second, 100 megabits per second. And there's been many standards over the last decades, and they keep increasing the speed. Now we're up to establishing standards for 400 gigabits per second and 800 gigabits per second. And 1.6 terabits per second is coming up next. And so the way they do it is it's a combination of clock cycles, like how fast you are able to put a packet on the wire, the inter-packet gap time, that is a thing, defining what that is. Channelization is another, where you're not actually sending data across a single lane. You're actually sending data across 4 lanes, let's say, 2 lanes or 4 lanes. I don't have all the specs in front of me. I don't know if we're up to 8 lanes or how many lanes that we're using, but they'll break a chunk of data and split it out and send it across multiple links at a time. I believe that's true. I think that I know you can do that. You can separate actually break up a frame into kind of like a cell, like a subframe,
Yeah.
into an even amount and spread it across the line. No, that's one strategy. Another strategy could be to send multiple frames across those parallel lines. And I forget the details because I didn't look this up before we had this conversation. But that's another way that they do it. So if you can't increase how quickly you're able to send a packet down the wire, you create more lanes so you can send more packets down the wire in parallel effectively. That's another way that they do it.
I just think of a highway.
Yeah.
Like
Yeah.
two lanes versus 5 lanes, you're going to get more
Yep.
throughput if you've got more
100%.
lanes.
100%. And then it's the responsibility of the Ethernet. I mean, to us as network engineers, we look at that and we don't know that it's been channelized. We just know that a frame goes in one side and out the other side. And that's all we see, because all the assembly, reassembly, channelization, all that stuff is handled by the Ethernet physical devices on either end. So that's how they do it. One of the challenges over the years has been physics, where you're coming up to the limits of what you can do with copper cabling, for example, which is why slower Ethernet speeds, you can send over longer copper distances. The faster the Ethernet speeds go, the shorter the copper is, because you're dealing with attenuation and crosstalk. Those can affect the signal and make them less reliable or just impossible to actually get a signal or get your frame, if you will, from point A to point B. And so you end up having limitations on the speed. All those things, again, are impacted by physics. Okay, so latency then, Holly. So we talked a good bit about bandwidth. Why is latency important? Well, as you said, it's the amount of time it takes to move a packet between a sender and a receiver, basically. That's what we were talking about. You and I happen to be geographically pretty close by, talking to someone else on the other side of the planet or across the country. That's going to be a lot more latency. Well, why does this matter? Do you know why latency matters? Do you know why we care about it?
I mean, I guess yes, but no. I mean, I think that's actually a good question, because you want to be as close to real time as possible. You want to, everything, I think in today's modern day and age, everything happens as fast as possible. So if I'm sending something, or for example, there's a lot of video nowadays, latency affects that. How, you want all of your frames or packets or whatever is being sent to arrive at the same time at the same place. And what would be ideal would be instantly.
So yes, all of those things are reasonable prognostication on your part. Yeah, you're thinking about it right, but it's more evil than that. It's more insidious. And the issue is tied with how network communications actually function. In your studies, you must have come across acknowledged versus unacknowledged protocols, TCP versus UDP. Did that come up or no? Yeah.
Yes.
Okay. So this is where latency comes into play in the most poignant way, is with TCP communications. So TCP, Transport Control Protocol, it is rules for getting IP packets from point A to point B. If a sender sends it over TCP, TCP defines, well, how do we know that it got there? And can I send more? And handles things. There's some level of error correction in there. And there's a variety of things that TCP can do for us. It is an acknowledged protocol, the keyword acknowledged. That is, I'm going to send you a packet. Okay, Holly, I just sent you a packet. Holly, did you get the packet? Say yes. Yak. Yes, you acknowledge the packet. And then I receive your ACK. Oh, she got the packet. Great. I'm going to send another one. Well, the longer our latency is, the longer it takes for this back and forth acknowledgement process to happen. And that can really slow down our throughput. It can impact our throughput through our pipe and make it difficult to fill the pipe with our conversation. Send you the packet. Wait for your ACK to come back. You send me ACK. Oh, good. You got it. I'm going to send another one. And now TCP doesn't just do one for one acknowledgement. It's not like TCP sends one and then gets one back. It's got this concept of an algorithm, a sliding window. The window will open, slide open to send as many packets as it reasonably can, and go, oh, I sent you 10 packets. Yep, I got all 10. Okay, cool. I'm going to send you another 10. Or maybe, oh, you got 10. I'm going to send you 12 now, or whatever, as the algorithm works. It's still clunky. It's still affected by latency, because there's still this, I'm not going to send you more until I get the acknowledgement back. And the higher the latency, the more it affects the conversation, and the bigger the pipe is. You and I could have 100 gigabits per second between us, but if TCP is really inefficient, or whatever the protocol we're using is really inefficient because of acknowledgements, it can be hard to fill 100 gigabits per second. That's what latency is all about at its core. And that problem is central to a lot of network engineering over the last couple of decades, honestly. So TCP has gone through tons of iterations, different variants, like, oh, well, we could make TCP more efficient in higher bandwidth scenarios if we tweak the algorithm like this. And there's a bunch of like thises out there. There's all these different TCP variants. But I think a bigger point is QUIC, the protocol QUIC, QUIC. Have you run into that?
I have not. I think I've actually heard about it on some of your previous podcasts, but I haven't dealt with it at all. Never came up in my work situation.
No, it's the I believe Quick will be the ultimate successor to TCP. It's designed to be quite a bit more efficient and to push a lot more traffic through a link. And we're not going to get into all of that today. I'm just going to highlight, because we're really coming up on time, that that TCP is probably going to be replaced by Quick, and already has replaced Quick in certain scenarios, especially with modern HTTP. You look at HTTP 2 and HTTP 3, which is slowly gaining prevalence. A lot of the specifications for it allow it to ride over Quick, QUIC again. And if you were to do a packet capture with something like Wireshark, you're going to see a good amount of Quick packets on the wire. And again, without getting into the details of Quick, it is about overcoming latency challenges on the global internet so that we can more efficiently use the bandwidth we have available to us as internet service providers and as network engineers. And so that's a point for a future podcast, Holly, how Quick is
Yeah,
different,
definitely.
maybe.
I've got some questions around that. But if we go back to latency, there's
Uh-huh.
um, all of these ultra low latency products being
Yes.
created. Um, what is ultra low latency? Because latency at the moment, we're talking milliseconds or like microseconds. It's
Mm-hmm.
seems pretty low to me. So, what is ultra low latency defined as, and how is it being done?
Ultra low latency is usually a term applied to data center switches.
Yeah,
So, and in your work, that may be where you're running into it. And the idea is, how long does it take for a packet, Ethernet frame in this case, probably with the products you're dealing with? Port to port latency is the term. How long does it take for that frame to hit the ingress port, and leave the egress port? And it's these days, I think we're measuring those in nanoseconds. Very
yeah,
low number of nanoseconds. And it's because of very specific use cases like high frequency trading,
yes,
where every nanosecond actually matters, because for a high frequency trading firm to make money, they need to make a trade before someone else makes a trade, and changes the game for them. No longer, if they make that trade after someone else does, it might change the price of what they're buying, and no longer do they make a profit. And so high frequency trading folks will look for any advantage they can get down into the nanoseconds. They care about things like the length of the cables that are running between devices, because there's some nanoseconds to be found in there. And also, this is what an ultra low latency product is all about. It tends to be something you sell into a data center environment for communications within that data center, because there's some cost driver that if they can,
yeah,
again, find some nanoseconds, it matters to their business.
yeah. I mean, that's the exact use case that I was dealing with, was financial services. So,
Yeah, I believe it. Yeah, it makes
right
sense. It
on.
makes good sense. Yeah, yeah. Um, what I don't have is like a specific definition. Ultra low latency is X number of nanoseconds. I don't know. I mean, I know what they're getting at, and it's a spec thing. You just look at the spec
Yeah,
sheets on a switch that's billed as ultra low latency, and compare it to things that are not that, not as optimized. The chipset's not as optimized. Maybe the internals of the switch in other ways are not as optimized, and so it gives up some milliseconds. Not that long ago, switches were, some port-to-port latency was still measured in microseconds. That might still be true. I haven't looked for a while. I haven't been switch shopping for a while. But nowadays, I think that we're down to nanoseconds for that
yeah,
port-to-port latency within a switch. Yeah. Yeah. So one other comment I'll make, Holly, on this latency thing is we talk about TCP and we talk about Quick. Well, I didn't mention UDP. What's that stand for? I don't remember anymore. But it's the unacknowledged twin of TCP, if you will. Unacknowledged data protocol? I don't know. I have to look. But UDP is used for things like voice. So like you and I chatting right now, we're on a Zoom chat, and we're probably talking, not necessarily, there's a variety of ways it could be done, but we're probably talking over UDP. Now,
mm.
wouldn't you think, Holly, that we would want to make darn sure all our voice packets get to each other? And so shouldn't we use an acknowledged protocol? Why would we be using UDP instead of TCP?
Well, I think, when it comes to voice, it's not as granular. As long as I can get the majority of what you're saying, it's good enough. I don't really need every single little bit to come through.
Well, I'll argue on that because if we drop some packets between us, what will happen is the quality of the call will degrade. There'll be some drops. The call won't sound natural. So I mean, you're also not wrong in that all of us that have dealt with phones, been on Zoom calls, been on Skype back in the day, we kind of got used to the call being not perfect and it was okay. But if you wanted a perfect call, if that was really important to you, which it is for certain people, they demand absolute perfection in their calls, even though it's going across the internet. It's going across UDP. Again, why UDP? I mean, don't we have to deliver every packet?
Well, it's it comes down to, I guess, sure, do you want every packet or do you want most of the packets quickly?
So the answer to the question where I'm leading you here is timeliness. So if you and I are talking, and because of congestion on the network, a bunch of the voice packets between you and I get backed up, waiting in a buffer to be sent. The conversation continues. I would just assume those packets be dropped. And then, there's a gap in our conversation. There's an awkward moment. And then the conversation continues. If we wait and wait and wait for hundreds of milliseconds or seconds for the traffic to get to us, it doesn't matter. The conversation's gone on and it's just weird. And all of a sudden, a bunch of traffic shows up, and you maybe have heard that on a Zoom call on occasion where all of a sudden someone's voice speeds up really fast, like that. And it's like, what happened? Well, the voice packets got trapped in a buffer and then they got sent all at once and it got caught up and it sounds weird. You might as well drop them. It just doesn't matter because time's moved on. The conversation's moved on. We don't need those packets anymore. And we don't have to have those packets. As you were pointing out earlier, unlike a web server application where you've got to have every bit for the transaction to make sense. If you drop a few voice packets, we can kind of make sense out of what we say, and then the compromise of quality. So, all right, Holly, we gotta kill this. But there's a couple of terms I'm going to throw out for us to study up on more. Jitter is one. It's related to latency. If the latency between you and I goes up and down, that's called jitter. Like we have really low latency and then we have high latency. That's jitter. And that sucks for voice communications. People that are voice engineers, voice over IP engineers care about jitter a lot. And then another term is buffer bloat. ISPs.
That's a new one.
Yeah, they love to have really big buffers so that they can say, we never drop any packets. Well, what they mean to say is, we have congestion everywhere, but we have buffers that are so big, we'll just stack the packets up and make everything wait until the congestion clears and then send them. And that's how we don't drop, which to us as users of that network feels like, why is everything so slow? Because stuff is stuck in buffers and not being dropped. When in actuality, if the ISP just dropped the packet, the experience, TCP would adjust and the things would feel a little bit more natural. So jitter, buffer bloat, a couple of homework terms if you're out there listening for you to go research those. They're really interesting topics that relate to bandwidth and latency.
UDP, user datagram protocol.
There we go. Thank you for looking that up. User datagram. I'm embarrassed.
It was somewhere in my head as well, and I couldn't find it. I know it's in there. Just it disappears over time.
Thank you for looking that up, Holly. Holly, if people want to find you on the internet, how do they do that?
LinkedIn. Just find me under Holly Metlitzky.
Excellent. I'm Ethan Banks. You can also find me on LinkedIn. And Holly and I are both also in the Packet Pushers Community Slack group. You can find that at packetpushers.net/community. Read the rules. They're very simple. And then sign up for the Slack group and you can talk to us in there. Join the N is for Networking pod channel and we'll be monitoring that. Thank you for listening again. Would you subscribe and then tell your friends about N is for Networking? You're going to find N is for Networking anywhere that you find your podcasts. If you have topics that you want Holly and I to cover, would you send us a message at packetpushers.net/follow-up or in the Slack group in the N is for Networking pod channel, and we will add your request to the list. We already got one in that's from someone who wants us to talk about EVPN and BGP and VXLAN, Holly, which is one of your specialties. So we should have fun on that one when we get around to that topic. And just remember, networking isn't hard. Other people figured it out, so you can too.